Hello, can you see the desktop? Are we live?
Yes.
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 Is anybody there?
Hello?
Hello, yes.
Hello. Okay. Okay, so you can all see the desktop, right? Okay.
Mhm.
All right. So I finally got the homework assignment. It took a long time to write it and organize it. So let me just show you. We've talked about it before, but let me just show you briefly now that it's actually there. So here's the homework assignment. It's got kind of a long description of it. As we said before, you're going to write two programs, a static analyzer and a parser. So I've downloaded the homework assignment. Here's the folder. Okay. You're going to write this file and that file. Okay. You have to write the parser and the static analyzer. Okay. It's language 7 that we've been working with. It's the same language. So let me open some. Okay. Here's the language. Okay. The language is written in a grammar. These are the productions of the grammar. Okay. If you look at the evaluate function, the interpreter, remember, the interpreter is written in the order of the language itself. So the interpreter is a sequence of functions that do things like evaluate expression. So you can evaluate an expression, but if expression is either an apply, an if, a while. So when you evaluate an expression, you look at the tree node that you're looking at. If the node is an apply node, you call evaluate apply. If the node is an if node, you call evaluate if. Then down here, you write the code for evaluate apply. Then you write the code here for evaluate y. So every one of these is a function. Okay. The parser is written the same way. Okay. Now, if I open the parser function, I've written a little bit of it for you already. So here's the parser. The parser is written as a bunch of functions that get the tokens for that part of the language. So here you're building the abstract syntax tree. Here you're walking the abstract syntax tree, but both programs are designed around the same idea. Okay, you evaluate a prog, but before that you have to build the prog. So you have this function that says get prog. So this gets from the tokens that make up a prog, and we know from the grammar that the tokens that make up a prog are there's either the tokens that make up an expression, or there's a left paren token followed by the prog token followed by the tokens for either expressions or functions, followed by a last expression token, followed by the closed parentheses. Okay, so the parser is written as a bunch of gets. Okay, now I've written a few of them for you here. If you get farther down in the code, I see here's the parts that I didn't write for you. You have to call get apply. You have to call get if. You have to write get if, get while, get there, get set. Okay, I wrote for you probably the two hardest parts. The fun and the lambda. Okay, the part that parses the fun and the part that parses the lambda are written. Okay, so here's the part that gets a fun here, and here's the part that gets a lambda. Those were written. Okay, then I partially wrote out get expression. Remember, expression is all these. You can see I started it for you. Say if you have a var, you call get var. If you have a set, you call get set. So I've done those two parts. I've sketched out those two parts of the grammar for you. To give you a sense of how to get started, you'll have to add a bunch more of these. You'll have to add parts for begin, print, Boolean expressions, arithmetic expressions. Okay, so I've sort of sketched a little bit of the parser out for you. Okay, so you have to complete. See, there's all these methods that have empty bodies. You have to write those. Okay. The other thing you have to write is the semantic analyzer. The semantic analyzer is written the same way. It's written based on this grammar here. Okay, so the semantic analyzer, instead of getting a production, you analyze a production. See, here's analyze expression. See, here was get expression. This guy is building the abstract syntax tree. This one, like the evaluator, is walking the abstract syntax tree. So here's the evaluator's get expression. See, evaluator evaluates expression. The parser gets an expression, and the analyzer analyzes an expression. Okay. Okay. The expression has a bunch of branches. Here I wrote a couple of the branches for you. Here I wrote two of the branches for you. But if here's what it looks like when you have all the code for all the branches. So notice that the evaluator, in a sense, is like a little bit of a guide for you to rewrite the parser and the static analyzer, because all three of these programs are written what we call syntax-directed programming style. All three of these programs, parser, the evaluator, and the static analyzer, are written using the grammar. They use the grammar as essentially a table of contents. Every production has a function. So you write it doesn't matter if you're doing the parser, the evaluator, or the static analyzer, you're going to have a function that does get. Well, the parser, it's get expression. The evaluator, it's evaluate expression. And the analyzer, it's analyze expression. And in the case of the expression, it's really just a branch. This is sort of a dispatcher that says, well, an expression is one of these. So the get expression, mostly, it's really a kind of the simplest one because it just calls one of the other ones. And you see that here, that get expression does nothing but call other ones. Here, evaluate expression either evaluates an apply, or evaluates an if, or evaluates a while, or evaluates a var, or evaluates a set, on and on. Okay, so it's just a dispatcher for all the other ones. The real work is done in those. Notice that this divides the code up into chunks. You write all your code by thinking in terms of what does that production do. So you would parse that production. You'd look at that production, it tells you how to parse it. You look at that production, it tells you how to evaluate it. Okay, so here's the evaluate if. You evaluate that production by evaluating the Boolean part. If it's true, you evaluate this part, but if this one's false, you evaluate that part. Okay, so that's done in the evaluate case. And you have to figure out what the analysis case would be. What's the analysis case for analyze if? And what is the parse case for get if? Now, from the grammar, get if should basically get expression, match closing parentheses. So when you write get if, you'll write it by looking at the grammar. Well, actually, it should start off by it should match with left parentheses, match the keyword if, then get an expression, match the closing parentheses. If that closing parentheses doesn't match, parsing error. So now you know that you won't have to match these because this guy here, get expression, won't send you down to get if unless it's already checked that you have that to begin with. So get expression will see that there's this part. Okay, so when you get down here to get if, get if really won't need to work. It'll need to get that token and get that token, but it won't need to check them because they can assume that they're there. But then it gets that, gets that, gets that. Then it needs to match that because somebody could inadvertently have forgotten that closing brace, or they could have had a fourth expression in there. So the get if will get expression 3 times, and then make sure that at that point it finds a closing parentheses. If it doesn't find a closing parentheses, it throws a parsing error. Okay, and for the evaluator, for the analyzer, what will analyze if do? Well, the analyzer is looking for what would be runtime errors. Remember, the analyzer is mostly looking for things like undefined variables. So when you analyze an if, what you really need to do is say, well, analyze that expression to make sure it doesn't have any runtime errors in it. Then analyze that expression to make sure it doesn't have any runtime errors in it. Then analyze that expression. So the analyze if is really simple. It's just going to call analyze expression on 3. It's a tree. It's analyzing a tree with if at the root. There's 3 sub-branches, and analyze if is just going to call analyze expression 3 times on that branch, and that branch. So analyze if is real easy to write. Analyze if will be very easy to write. So it's going to be 3 calls to analyze expression. Okay. The trickier ones to write are going to be the trickier ones. Everything is tricky has to do with functions. So the tricky ones are going to be like analyze apply, analyze lambda, and I think I wrote analyze fun for you, but analyze lambda and analyze apply will be the slightly tricky ones. Almost everything else is pretty straightforward. You're mostly just looking for undeclared variables. Okay, so this is the single most important idea of the programming assignment, is that all the code for the evaluator, the analyzer, and the parser, all of them are syntax driven. The code is driven by this grammar. So there's a function for every production, and you write your code thinking, which is a nice way to organize the code. Because when you're writing these guys, you just write them one production at a time, which means you can also debug them one production at a time. You can write the code for parse if, and then you can write a program that's just a program that's just an if statement and make sure it parses. Okay. Then you can write the parser for a while. Then you can write a program that's just a single while expression and make sure it parses. Then you can write the code for parsing of var. And then you can write a test program that's just a single var expression and make sure it parses. So you have a way of breaking your program down into write one piece at a time. When you write the parser, just write one of these at a time. Do the simple ones first, like if, while, var, set, begin, print. Leave the hard ones, apply, lambda for the end. But write one of these functions, write one part of the parser at a time, write a test case that's just that one expression that you just wrote and make sure it parses. Then you could write the analysis case, like suppose you wrote the parser for if. Then you could write the analysis of if. Well, you can't really write the analysis for if because the if statement's going to have things inside of it. Unless you write a really simple if statement that just says something like if true, then 0 or 1. Okay, so the analyzer, you'll probably have to write a few pieces of the analyzer before you can really test it. So you'll probably need, I suggest in the notes that you start off with these 2. Write the analysis for those 2, because you can test them right away. Like you can just test that you can set a variable to a number, or you can set a variable to a Boolean. So write the analyzer for those 2 first, and then do the analysis for if and while. Okay, and then do the analysis for the arithmetic and Boolean expressions. Then you can start testing. And then write the analysis for apply, lambda, and fun last, because those are the hardest. But write your code using this as your guide. The grammar is your guide, and you're inherently dividing your program into pieces. So write one piece, as much as possible, write a piece and test it. Now let me show you another part of this assignment. I wrote a demo version of it so that you can kind of play with it. Okay, so if you go in here, here is a demo version of the parser and the analyzer and everything all in this jar file. And if you double click this thing, it runs. Okay, so this is a prompt. This is a REPL. So for example, I can type an expression in this language. So var x5. Okay, now this is a verbose version of the program. You see all the debugging information that was done. So for example, the analyzer created an environment so it could check variables. And then the interpreter created an environment so it could store variables. So there's actually two environments, one for analyzing and one for interpreting. So for example, if I say var x6, okay, notice I get an error. The analyzer said you're redeclaring a variable. So I can't declare a variable two times. Okay. Now notice that that didn't update the global environment because since this was an error, there was this it didn't update this global environment. Now if I say var y3, now I'm going to get, see, two. Now my global environment's got an x and a y. The analysis environment, and you needed the y in it to just, you know, when you read the notes to the assignment, you'll see that the analyzer needs temporary environments to do its analysis job. So the analyzer is creating environments that are used temporarily, that while the REPL is building the global environment. Okay, and then I can do something like I can declare a function. Oops. Okay, there's a function that just adds. Okay, so now I've got this function. Okay, now I can do something like I can apply f to an input. Okay, all right, and this is the verbose version of the interpreter. So it shows you how when I applied f to 3, I created there was the global environment. There's the activation record, the activation environment for binding the parameter 3 to the actual parameter 3 to the local variable x. That's bound in here. Then it did the evaluation. You know. Now look what happens if I call this function with too many parameters. See, there's the analysis error. Notice that in earlier versions of this language, if you had too many arguments for a function, that would be caught by the interpreter. It can't be caught by the parser, but it was in the past caught by the interpreter. Now it's being caught before the interpreter runs. It's being caught by the analyzer. The analyzer said there's too many parameters to that function. This is, now, catching errors like this before the program runs is really important, because catching errors at runtime is dangerous. That's one of the big problems with JavaScript and Python. If you write many thousands of lines of Python or JavaScript, you may have a bug lurking in there that you just never saw happen. You know, maybe you have an application of a function that's got too many parameters. Maybe you redefined the function at one point and forgot that one of the applications calls the function with wrong number of arguments. If that function is very rarely called, maybe it's only called when a certain error condition comes up, you may not know there's a problem there until you hit it at runtime. These kinds of problems should be found at compile time. Now, we don't have a compiler, but we still have what we can call analysis time. Analysis time is after the parsing, but before the interpreter. It's essentially what is equivalent to compile time. You know, the compiler would parse and then generate code. In our case, we parse and then analyze. When the compiler generates code, it does the analysis at code generation time. In our case, we're going to do the analysis before we run the interpreter. If you go back to the homework assignment, you see what I mean? if here's a test program that's going to test your code. And what it's going to do is it will take, here's a whole bunch of strings in the language. So here's a whole bunch of strings in the language. There's an array of strings. You'll take an element, you'll take one of those strings and you tokenize it. Then after you tokenize it, you give the tokens to the parser, and that builds the abstract syntax tree. After you add the abstract syntax tree, well, here that we print it out, but after you have the abstract syntax tree, then you analyze the abstract syntax tree. Okay, so after you build the abstract syntax tree, you analyze it. If the analysis program returns false, that means the program didn't analyze properly. The analysis is a Boolean operation. It returns true or false. So if it did not analyze, I just skipped the interpreter step. See, here's the interpreter step. So this continue would just say, well, if we fail the analysis step, we don't interpret the program. Okay, so that would be a compiling failure. Okay, that'd be like compiling failure. Now, in our case, compiling failure is possibly a parse error. Okay, if we go back here to this demo, I can also generate parsing errors. So for example, I can say var x for 5. Notice that's a parsing error because var only takes a variable and a value. There shouldn't be a second value there. So it expected there to be a close parentheses where the 5 is. See, it expected a close parentheses where the 5 should be, because after it should be var, variable, expression, and after that expression should be close parentheses, but it found 5. That's a parse exception. If you get a parse exception, you don't do, now the parser throws an exception. So if you don't parse, you just get caught with a parser exception. The analyzer does not throw an exception. I'll show you why in a second. The analyzer returns a Boolean. The reason you don't want it to throw an exception, watch this. Suppose I say var x y. No, var x w. Okay, notice I got, that wasn't a good example. Here, let me draw another one. Var x w. Again, okay. Okay. Oh, I'm sorry. I know what I'm doing wrong. Yeah. Notice I got 2 analysis errors. I kept using var. I should have been using set. There's 2 errors in this line. Now, if we were throwing exceptions, as soon as you caught one error, you'd be, you wouldn't see the second error. And that's the case with parsing errors. When you find a parsing error, you just report it, and people need to fix that error and just then try to parse their program. But with analysis errors, we want you to, when you find an analysis error, to keep on going to see if there might be other errors. Okay, so for example, this set A, A should have been declared ahead of time. So I have an undefined variable A at character 6, but then I also have an undefined variable B at character 8. So I have 2 analysis errors. So when you're analyzing a program, you don't throw exceptions, because if you find one analysis error, you want to keep going on to other ones. Here's another example. Suppose I have if, say, true, okay, var x c set else set p to q. Okay, now there's actually several errors in this program. There's an undefined variable c here. There's an undefined variable here and undefined variable here. So when you're analyzing this, first you're going to analyze this branch, but that comes out okay. Then you analyze this branch and there's an error, but you don't stop the analyzer. You just set a flag that says that this whole analysis thing is going to return false because there's a problem, but then it still goes and checks this guy and sees that there's more errors. Okay? So this generated 1, 2, 3 analysis errors because of the C, the P, and the Q. Okay? All right? Okay. So a parser and a tokenizer throw exceptions because once you find one bad token, there's really not much point in continuing on and looking for more bad, for anything else. And once you find one bad parsing error, there's really not much point in going on. But with the analyzer, it's worth going on. Yeah, there's no real compelling reason why, because you found one error, you should just stop. You might as well just analyze the whole program and let the user know all the errors. So the analyzer doesn't throw exceptions, it returns a Boolean. If there's at least one error, it returns false. But if there's more than one error, it should report as many of them as it can find. Okay, so the analyzer returns a Boolean. If it's not successful, then we skip the evaluate stage. The evaluate stage throws exceptions. Again, if your program did something wrong while it's running, there's really no way you can continue. If you really wanted to, you could probably continue parsing if you found a parse error. It's kind of hard to do, but modern parsers like in C and C++ and Java, they do that. Just because they find one parsing error, they don't stop. They continue to parse. But it's a little bit tricky to do that. So we're not going to try to have a parser that continues on after it finds one parsing error. Same with the tokenizer. If you wanted to, you really could have the tokenizer, even when it finds one token error, continue on and try to find more. But it makes things once it's got found one problem, it's a little bit hard for it to keep track of what's going on. So for our point of view, the tokenizer and the parser is just easier to make them throw exceptions. The evaluator, there's no question. The evaluator has to halt when it's found a problem. The analyzer is the one that we can that we can not have throw an exception. It's not hard to make the analyzer do this. It's not hard to have the analyzer continue to analyze even after it's found one error. Because these things are static errors, an error in this branch of the code really didn't have any effect on this branch of the code. That's not true with tokenizing and parsing. If something didn't parse over here, it could have a huge effect on how you parse what comes afterwards. If you think about it, it can be really messy to find a parsing error and try to continue parsing. It actually is one of the things that make modern parsers really difficult. But most people like it that when you compile a C program, it tells you what all your errors are, not just your first error. Okay, so it's something that makes modern parsers difficult, but they try, and they don't always do a good job of this, but when they find one parse error, they kind of try. Now, C++ is famous for if you have some stupid little parsing error, you can generate 1,000 error messages, because when it tries to continue parsing, it doesn't do a very good job. So even in the C++ compiler, if there is a parsing error, it's not unusual for the C++ compiler to get completely lost while it tries to continue parsing your program and just start spitting out false error after false error after false error. So we keep our parser simple. If it finds one parsing error, stop. Same with tokenizer. As soon as you find a tokenizing error, stop. But the analysis, they're not coupled. If there's an analysis error in there, that really doesn't have any effect on the analysis error over here. So why not, if this thing failed analysis, go ahead and check this one. So your analyzer won't throw exceptions. And this interpreter that I wrote here, this demo program, use it as a way to get familiar with how this stuff works. You can do all kinds of, you can just go here and do all kinds of dumb things, like misspell something. That's an unexpected token. There is no var, V-E-R token. What happens if you do, see, I forgot the closing parentheses. Now your programs eventually have to do this. Your parser is going to have to detect that there is that there was an unended parentheses there. Now, what about if I put 2 extra parentheses there? Okay. Oh, that shouldn't have parsed. See, there's extra closing parentheses there. I'm not sure why that parsed. I have to look. That might be a little bug in my parser. That shouldn't have parsed. Let me try another one. If true, 2 or 3. Ah, so I have a little bug in my parser. The parser should have detected that there was an extra token there, right? So what happened is the parser got up to there and didn't detect that there was an extra token there. I know it does in some places. It will detect two extra tokens in some places, but right now this one isn't. Okay, if you do this, see, now that had unbalanced parentheses and it's unexpected. Now notice that it's this. There should never be two parentheses. Oh, there should never be in our language two opening parentheses in a row. So this thing, that's a parse error. It found a parentheses, an opening parentheses right after an opening parentheses. Okay, so that was a parse error. Okay, so you can play around with this language. Uh, you you can play around with the interpreter and do little experiments to see how it should act. When your code is completely done, the interpreter is this program here, but it won't compile and run until you have this parser completely done and this analyzer completely done. So you can't really use this REPL to test your program. Well, you can, but you have to have it all completely written. Then you can use the REPL to maybe test it like I'm doing here to see how well it works. But you can't use it for unit testing. To unit test, you have to write your own little test. Though I do give you a bunch of test cases for unit testing. If you look at this program here, here's a huge number of things that should all cause analysis errors. Oh, I'm sorry, parse errors. Notice that I just did almost every kind of thing that you could do wrong. A single parentheses, an empty pair of parentheses, parentheses var with nothing after it, parentheses var with a closing parentheses, parentheses var with, yeah. And see, actually, I was missing a test case. See, I should have put a test case in there. You can see now I should have had a test case that looked like this. That's notice that if you don't have test cases, you tend to have errors that you should have. I tried to put a huge number of test cases in here, and I actually missed a few test cases. I should have put that test case in there because my parser probably would not have passed that. There should be a parse error there. Okay. So I give you a huge number of tests. Now this is testing everything. So when you're building your code, you want to pass these tests when you're done, but you need to write your own little tests because when you start writing your parser for var, you need to just do those tests. When you write your parser for set, you only want to do those tests. Then you can move on to maybe do if. When you write your parser for if, then you want to do those tests. When you want to do, when you write your parser for while, you'd want to use tests like these. So I lumped into one place all the tests that I was using. There's actually over 100 of them in here. So there's just a huge number of tests of things that you should check for in parsing errors. And then there's also a program like this for the static analyzer. Here's all things that should throw analysis errors. Like this is an undeclared variable. That's an undeclared variable. That's two undeclared variables. That's an undeclared variable. So yeah, it starts off with lots of examples of undeclared variables. Actually, most of the errors here are undeclared variables. By far and away, the most of them are undeclared variables. Okay, so there's a whole bunch of just ways to generate undeclared variables. And then there's also a few things like an undeclared function name too. So there's examples down here where, like here, apply f to 0. Well, f's never been defined. So that's an undefined function name. There's another undefined function name, undefined function name. There's another one with an undefined function. The difference is here it's just a single apply. Here it's apply inside of a begin. Here it's apply inside of a prog. So I'm kind of testing that you're checking apply in different contexts. This is in the context of a single expression at the top level. This is in the context of a begin expression at the top level. This is an apply inside of a prog. This is an apply inside of a begin inside of a prog. So, you kind of test all possible ways an apply with an undefined function could be there. This has an empty environment. This has two environments because there's the global environment and the begin environment. Okay. Again, this one has one environment, just the global environment, and this one has two environments, the global environment and the begin environment. So they're slightly different cases. There's slightly different cases going on in here. So there's huge numbers of these tests. There's about 50 of these tests and over 100 of these tests. You can't expect to pass these programs until you've done everything, but you can pull pieces of this out and write your own little tests using just pieces of this to test. Like when you've got set done, you can test those. Okay. When you've got begin done, you can test. When you have begin, var, and set done, you can test those. Okay. So eventually you want to pass all these tests. Eventually your code needs to pass all these tests, but you can't just write your code and expect it. Don't write your whole program, then run this and see what happens. You'll just end up with thousands of errors. So build your program up function by function. Remember, my suggestion is to start with set and var. Parse set and var, analyze set and var, then go on to something like if and while, parse those, analyze those, and build your program up slowly, and test just whatever little pieces you've written. Okay? Okay, so that's the homework assignment. Remember to use the REPL to play around with the language to get a feel for what it looks like, what the language feels like. You can also, notice that whenever you do something in the REPL, it gives you a picture of what you did. So the REPL is always, every time you type something into the REPL, it shows you what the parse tree for that expression looked like. Okay, so I did a bunch of simple examples. You can delete them just by double-clicking clean. You can also run script files. If you want to, you can do your testing by writing little script files. And if you drag and drop them onto the CMD file, they run. But notice that it just ran in a pop-up window and died, so you don't get to see what it did. If you want to see what it did, you need to open a shell here. Okay. Open a shell and run the batch file. The batch file just launches the jar file for you. Okay, so you can't, because of a Windows kind of weirdness, if you just double click on the jar file, it doesn't work right. So I had to write a batch file to launch the jar file. The batch file just has one line in it. It just launches the jar file using the jar command, and you have to do it this way. You can't. Jar files are double clickable in Windows, but there's a little catch. This is a weird little catch. A jar file only works if it's a double clickable GUI program. You can't write command line programs and make them double clickable jar files. You have to launch them in batch files. Since this is actually a command line program, it needs to be launched in, see, it's a command line program. See, it runs in the command prompt, okay? Because of a weirdness of Windows, if you have a Java program in a jar file and it's a command line program, it's got to be launched by a batch file. You just can't double click on the jar file. But if the jar file holds a GUI program, you can just double click on the jar file and it'll launch the GUI. Okay. So if I want to run this script file, I have to type the name of the command file, then the name of the script file. Okay. And then see, it ran the script file. Okay. So there's the running of the script file. This thing dumps all kinds of information. It's real verbose. It dumps the tokens, then it pretty prints the program. Then it shows you all of the analysis environments. Then it shows you the interpreter environments. So it's a really verbose output that can be useful if you're trying to figure out what your program should do. So this thing shows you what the tokenizer created, shows you what the parse tree looks like. It pretty prints the parse tree 3 different ways. Then it shows you the global analysis steps, the static analysis steps. Then it shows you the interpreter steps with the environments. And then there's the final result. Okay. And then it also draws the parse tree over here. Okay. And then after you run a script, you could just clean up and the script file goes away. So if you want, you could have test scripts. Okay. Yeah. If you want to test your program with test scripts, you actually won't be able to use test scripts on yours unless you write the whole interpreter, because this jar file was built by this file, and that file won't work until this file and this file are correct. Okay, so you really can't build your own interpreter until you're kind of done. But when you're almost done, you could build the interpreter and maybe use bat script files to do some last checks with it. But the majority of the writing of your code and the majority of the testing of your code is going to have to be done by writing your own tests. Basically, take this program here. See, like the parser error. Take this program here and just make a copy of it and just delete the vast majority of these tests. You know, what you'll want to do is delete almost all those tests, so there's just a couple tests in there. Compile, run it, get a couple tests running, then add tests to this one at a time. Just build this program up one test at a time. Make a copy of the original program and make this your unit testing program, where you just add one more test at a time. Just add simple test after simple test and build up your code one, like, you know, you can add a simple test for if. Yeah, maybe you test if without the closing parentheses. So there's a test for parsing if without a closing parentheses. So you can build up a list of your own, or you can use mine, but you'd want to delete the majority of them and just have a small number of tests and just grow your list of tests as you're writing your code. Okay. And same with the static analysis. After you've got the parser working, take this file, make a copy of it, then delete almost all these tests until you have just a small number of tests. Get the first couple tests passed, then add tests one at a time to this, little bit by little bit, and grow your language and add more tests, grow your language and add more tests. That's a pretty effective way to write the assignment like this. You will be writing quite a bit of code. Notice that the interpreter, which is already written, I'm sorry, not that. The interpreter is a good sense of what's going on. Okay, this is the interpreter. It's 600 lines of code. The analyzer is not that many. The parser is more than that. The parser will be more than that. The analyzer will be probably about half that. But the code is a lot of boilerplate code. I didn't try to write this code in the most absolutely elegant way possible. I tried to make it more follow your nose and do the obvious thing so that these functions would be easy to write. That's not a bad strategy for getting this working. Write these functions one at a time, just get each one working. Don't worry about trying to write the most elegant code. The thing that makes this thing work mostly is the fact that this is your table of contents of the code. The fact that the code is broken up into that function, that function, that function, that function, that already makes it pretty well structured. So then you can just write your functions one at a time, but they will be verbose. This is not the most elegant style for writing code. So you see the interpreter is 600 lines and there's a lot of very repetitive looking code in here. The analyzer will be fewer, the parser will be more. Because the parser has to do a lot of very repetitive testing for parsing errors. So the parser ends up being pretty repetitive code. But don't worry so much about the repetitiveness of it. Get it working. Yeah, get it working. After you get it working, if you want, you can sit back and stare at your code and think if you can make it a more elegant. To make the evaluator as easy to read as possible, I actually left things pretty verbose. You know, I didn't try to find places where I could write functions that would abstract some of the code that's repeated in here. I tried to make it read more like a description of the code than trying to make the code the most maintainable code possible. In the real world, code should be written in a way that makes it maintainable. Here, I'm really trying to write it to make it readable. Okay, so I'm really trying to make things as readable as possible. You will find repetitious code in here, and that's okay with yours too, because you're going to end. You need to write one function at a time, get it working, then go on to the next function. Yeah. If you want, after you've gotten all the functions written, then you can step back and maybe think about a better architecture for things, but you may not have time to do that. Yeah. The real goal is to get the code working and debugged. Okay. Let's see. Read the description of the assignment carefully. There's quite a bit of hints in here about how to write the code. Okay, so anybody have any question? Any question about the homework assignment? I mean, if you have questions as time goes along, you can always send me an email or ask me to meet with you. But does anybody have any question right now that you can think of about the assignment? Okay, nobody, no, okay. So if you have any questions at all, please let me know. Let's see, I'm trying to remember if there's anything else I wanted to point out to you about the assignment first before we. Oh, there's one little thing I point out. If I run the demo program, notice I'm putting new lines in here. So that expression is really 3 lines of code. Oh, I forgot the. Oh, I can't put /ns in this interpreter. Oh, I can't do that. I forgot these aren't strings. Does anybody? Let's see. Oh, yeah, I forgot you can't put /ns into the input of a command prompt.
There's some key combo that lets
Okay,
you
let me run one of the
insert.
scripts. Let me do it with the script files. Okay, notice that the script file is 6 lines long. Okay, let me put some errors in here. Okay. Okay, so I put a bunch of errors in there, undefined variables. Now let me run that script. Okay. So here's the analysis error. Notice the analysis errors say undefined variable z at line 4. See, it's like notice that I modified this language, the tokenizer, to keep track of line numbers of all the tokens, which you can use in your error messages. So on line 4, there's an undefined variable z at character position 25. Okay, and if you look at my text editor, you'll see that I'm at line 4. Oh, I'm probably off by 1 in my counting. I'm at character 20. No, 25. See, I'm at line 4, character 25. See, undefined variable z at line 4, character 25. So the tokens in this language, in this homework assignment, I rewrote the tokenizer so that the tokens keep track of, and you can see that up here, every token keeps track of what line and what character it came from. So every token keeps track of the line and the character it came from, which is very nice. This is how a real tokenizer would work. So you can give very nice error messages and say on what, that way if there's more than one z in a line, you can say exactly which z caused the error. So the u at line 5, character 25, okay, the u. And then there was another, let's see. Oh, I put a G here. I thought G was an undefined variable. I meant this to be, I meant to put an H there. I was trying to create another mistake. So let me go over here and put another mistake in there. Okay. And then I can rerun it over here. Okay. I'll rerun it. Okay. Notice I got another error, undefined function H at line 6, character 26. So there's that guy. See, line 6, character 26 is the undefined H. Okay, so now that means every token now knows what line number it came from and what character it came from. But for the parser to get that information, you have to store the tokens in the parse tree. So it used to be we only stored this string in the parse tree. So in the earlier programming assignments and in the early examples in class, the parse trees, which are drawn, here's the parse tree. The parse trees held these strings. Well, now I didn't draw it here, but the parse tree actually holds the string, the line number, and the character number. So I didn't draw it in the parse tree. It would have cluttered the parse tree, I think, up too much to draw the two numbers here. But you have to realize in your code that the parse tree nodes no longer hold strings. The parse tree nodes hold tokens, and the token has 3 fields: the string and the line number and the character number. So now a token actually holds 3 fields: a string, a line number, and a character number. And then the parse tree holds tokens in the nodes. So that's a little bit, you have to be a little bit careful. You have to make sure you remember that the things have switched now so that the parse trees hold tokens, not strings. Okay, the parse trees no longer hold the strings themselves. The parse trees hold the tokens, which hold the strings. So that's a little bit different in this assignment than it was in the previous one. To make that work, I had to modify, I'd made little changes in the code all over the place. So I changed the tokenizer and the tokens. I changed the tree to hold tokens instead of strings. And I had to rewrite the evaluator so that as it walked the parse tree, it realized that every node in the parse tree held a token, not a string. So that had to make a little change in the evaluator. And then also had to, you have to account for that when you write the parser. When you write the parser, you're not going to write the parser to literally build up this tree like this. You're going to have to remember that in the nodes of these nodes, you put the tokens in the nodes. Okay, and then when I wrote tree to dot, which draws those pictures, when it walks the tree, it extracts the string from each node and puts the string in the dot picture, not the actual token. Okay, so that's one little thing for you to be aware of, is that there's been this small change that now the trees hold tokens, and the tree nodes hold tokens, and the tokens hold line numbers and character numbers, which is real nice because now you can write very realistic looking error messages about how there's an error at such and such line and such character in the line. Okay, and if you want, you can look at the code for the tokenizer to see how that works. I stole this code from that one online book about interpreters. So most of the idea for this code came out of his tokenizer, and it's a very elegant tokenizer. It works really well. Okay, so you can, if you want, you can look at the code for the tokenizer to see how it does that. I think that's the last idea that's in this assignment that's new. Okay. Oh, this program is the same test program that we had for language 7 when we started doing language 7. It doesn't play much role in this assignment as just a check that when your parser is done, you haven't screwed up the abstract syntax trees if this program runs and generates this output. So this program, this program does not generate any parsing errors or any semantic errors, static errors. This program has nothing but correct programs in it. But what it's really doing is it's testing, if you run this, it's really testing that you built good parse trees, because this tests lots of features of the language. So the test does not, it tests your parser real well. So this tests your parser, but it doesn't in any way test your analyzer. And it even doesn't test your parser in some way, because it doesn't test any of your error messages. It tests that your parser builds a correct parse tree, builds a correct abstract syntax tree, but it doesn't test your parser for generating errors. That's where this tests your parser errors. Okay, so this one, you want to make sure that this program, you want to make sure that this program runs. Its output should look like this. You can just compare the output of your program to that program. See, this is the very verbose output. This takes the program, it doesn't spit out the tokens, but it prints the program, inline prints the program, then shows all the environments that the interpreter is using. So it goes through all the environments that the interpreter uses and gets the final result. Okay, so it's a pretty verbose output. So your program will pass these tests if your program has a proper parser. But again, it doesn't test for your parser error messages. It just tests that your parser builds correct abstract syntax trees for correct programs. Okay, so that's the last piece of this assignment. So that test program is useful for make sure that you haven't goofed up the abstract syntax trees. And this one builds the REPL, but again, it'll only really work if this program is complete and that program is complete. Okay, all right. Okay, so that's the programming assignment. Okay. Let's go look at, let's start talking about some new, we started talking about language 8. Okay, and we're talking about nested functions. And here's what I think we should do. We should take a detour into the scheme programming language, because I'm not sure how many of you have ever seen a language with nested functions and seen how nested functions actually get used in real functional programming languages. So scheme is the language that's closest to our language. The language we're writing is very close to the syntax of scheme. So I thought, okay, if we use scheme, there's a nice introduction to scheme. This is what the book, there's a website for, this book is actually the scheme standard. This book is not a book on teaching scheme. It's a book that actually defines the scheme standard. But it's got a very nice introductory chapter. This chapter 2 is I think one of the better introductions to scheme out there. The rest of the book is a very technical description of the scheme language. Okay, so it's not a book that really teaches you much. It has a very good intro to scheme. Sorry. It has this very good intro to scheme, which is about as much as we need. It's a very basic introduction to scheme, and then it goes into the definition of the language itself. Okay, so there's a huge jump from chapter 2 to chapter 3. You know, chapter 2 is very introductory, chapter 3 is very advanced. Okay, chapter 3 goes into things like continuations, continuation passing style, syntactic extension. These are very advanced topics. So there's a huge jump from chapter 2 to chapter 3, but chapter 2 is a very nice introduction. And it's got homework problems in it too. The guy who wrote this, he even put nice exercises into chapter 2. So what I want you to do is read chapter 1, which is only a couple pages. There's not much in it. But read this chapter 2. Read chapter 2. It's got a nice introduction to scheme, and it's got very good problems. See, like there's an exercise here. Okay. So in the homework, I told you a few that I think you should look at. There's 1, 2, 3, 4, 5, 6 homework problems there. You know, think of this as just, you know, this is just studying. Read through this chapter, make sure you think about those problems. If you want, you know, we can look at them in class next week. Yeah, we could look at some of these. If anyone has questions about these problems, we can look at them next week in class. So these are nice little problems to help you think about functional programming in the Scheme language. Here's where you can download a copy of Scheme. Now, here's what it looks like. Here's 2 versions of the Scheme interpreter. If I run this one, it's just like the REPL we wrote. See, here's the Scheme language. So I can take the sum of 1, 2, 3, see, plus 6. Or I can, now I don't say there to define a variable, I say define. So define x to be 4. What's x? It's 4. So instead of using the keyword there for defining things, here we use the keyword define. I can define a function like this. Define f to be lambda. Now in our language, we would write lambda x, where I'm going to write the squaring function. Okay, so I would write it this way. In our language, I would write this, that lambda x, that's the input function, input variable, and then I'm going to take this product of x with x, and then that closes the lambda, and then this closes the define. Okay, in this language, you put a pair of parentheses around the parameters. Okay, so you say lambda, then you put a list of parameters inside parentheses, and then you put the body of the function. Okay, all right, now I've got my function f. So I can, now in our language, we would say apply f to 5. In this language, you don't have to say apply. Okay, you can just say f of 5. So f of 5 is 25. So our language is close to this language. We would use there instead of define. We use lambda. I mean, I copied our language mostly from Scheme. So our languages 7 and 8 are essentially a kind of simplified version of Scheme. Okay, and Scheme is Lisp. So what we're typing here is really kind of Lisp-like. The one big difference is that when you apply a function, you don't have to say apply, and you put parentheses around the parameters. Okay, so you say lambda parentheses. Like if I want a function of 2 variables, suppose I'm going to take a function of 2 variables. I would write it this way: x and y, and then maybe I want to take the product of. Okay, I'll make the function add the 2 variables. Okay, so now I would say g of 3 and 4 is 7. Okay, so lambda, list of parameters inside parentheses, then the body of the expression. Okay, very similar language. Use define instead of there, and use lambda to define functions just like we do, but with the parameters having parentheses around them. Now, I can do these almost in our language. Like if I go to the REPL in our language, okay, plus 1, 2, 3, see, just like Scheme. I can say there, I say there x4, okay. So instead of saying define in our language, I say there, okay. And then if I wanted to find the function f, I would say var instead of define, f to be lambda. I just put x by itself here. That's the parameter. Then times x. We'll see, do I need one more? Okay. Oh, what did I do wrong? What did I do wrong there? That didn't parse. But I'm trying to remember. Oh, I'm sorry. In this, we use fun for defining. We have to define functions with a separate keyword. I'm sorry. We have to define functions with a separate keyword. Ah, I drew a blank there. Yeah, see, they use the same keyword for functions and variables. They use define. Our language 8 is like scheme. Our language 8 will be able to use var for both functions and variables. But in language 7, I have to use a different keyword for defining functions, because language 7 makes all functions global. There are no local functions. That's the difference between language 7 and 8. Scheme functions are local, so you can have local functions inside of functions. Okay, so then in our language, I apply f to 5. Okay, and I can define a function of 2 variables, g. Now I just put the variables one after the other. Oops. Okay, there's my function of 2 variables. And then I'll take the sum of the 2 variables. Okay. Right. So our language, see how our language looks a lot like scheme. So other than having those extra parentheses here and here, scheme uses those parentheses. Scheme uses define. Our language uses fun and var. Language 7 uses var for variables, fun for functions, and language 8 will use var for both, like scheme. Okay, and then over here I can apply the new function. I say apply g to 3, 3, 4. Okay, all right. So you can see there's a lot of similarity between our language, scheme, and our language. Scheme's got a lot more features than our language does. Everything our language has, scheme has. The scheme has a lot more than our language does. But the syntax in our language is very similar to the syntax in scheme. So for example, I can say if true 3, 4. See? If false. See? So if statement is an if statement, just has 3 branches, just like our if statements. So over here, I can say if true 3, 3, 4, that gives me back 3. And if I say if false, okay, right? If I misspell false, undefined variable, false. See that it thinks it's a variable there. And if I go over here and I misspell false, pretty much same thing. False undefined. Cannot reference an identifier. See, the language is both. They didn't know you misspelled false. They just see an identifier that's not been declared, so they give you an undefined variable. Okay, right? So, right. So, scheme is a good substitute for our language because it's a real, honest to good, powerful programming language that's used quite a bit in, especially in the research world. Scheme isn't used much in industry, but it's used a lot in graduate programs and in research. It's a great language for doing research in programming languages. So scheme is really popular. Okay. Now so what I want to do is I want you to read this chapter on scheme. We'll do some more scheme today in class, and I'll show you. I'll kind of give you an overview of what this is about. But read this overview of scheme, okay? and do these few exercises that I mentioned here. They'll really get you thinking about scheme, and I'll give you some more exercises as we go along to give they're good practices to work with scheme. Download scheme, okay? Now, I pointed, there are two versions of scheme. There's full-blown, it's called Racket. The program you're going to download is called Racket. There's a minimal version of it and the full-blown version. I thought the minimal version would be good enough. It's a small download. It's like 10 megabytes. The full-blown version is like 100 megabytes. But I might be wrong. The minimal version might be too minimal. I actually, on this computer, have the full-blown version installed. The full-blown version has two interpreters, this baby one, but then it also has a very rich, powerful interpreter. If you've ever seen the interpreter that comes with Python, this is much more like the Python interpreter. You notice it takes a while to launch. There. This is called Dr. Racket. It's a great piece of software. It's a full-blown IDE for working with scheme. Okay. Up here is where you can type code, and then down here is a REPL. So you have two places where you can. It's a lot like, some of you use Dr. Java, right? If you've ever used Dr. Java and you want to know where it came from, here's where it came from. Dr. Java was written by the people who originally wrote Dr. Racket. And you might notice that the Dr. Java looks like this. And the reason is that Dr. Java was written by the people who wrote this thing. Okay, and that's why it's called Dr. Java, because they called theirs Dr. Racket. I don't know why they called it Dr. Racket, but this has been around for 20 years. So they called this guy Dr. Racket. And then when they wrote a Java version of this thing, they called it Dr. Java. But it's the same group of people. The Dr. Java IDE came out of the Dr. Racket thing. But Dr. Racket is actually much more powerful than Dr. Java. This thing does much more for scheme than Dr. Java. Dr. Java is a very basic Java IDE. This is actually a fairly powerful IDE for the scheme language. The REPL is down here. Okay, so here is the REPL. If you just want to type piece of code and here's a weird, I forgot about this. Racket scheme is actually a collection of languages. So you have to tell Dr. Racket which version of scheme you want to use. So you go up here and you say choose language. Okay, and I'm going to just choose the regular Racket language, which is the same thing as scheme. So I'm just going to choose regular Racket. These other languages are used for teaching Racket, but right now we just want to use the regular Racket language. So then you click OK. Okay. And then now this interpreter should be running the Racket language. Let's see. Why not? I've messed up the interpreter because I forgot to set the language first. Okay, click the run button. I think that resets it. There. See, now I've finally got the interpreter running. So I have to set the language first. I have to choose a language. I think after you choose a language once, I don't think you'll have to choose it again. I haven't run Dr. Racket in this account before. This is an account I use for the classroom, and this is the first time I've run Dr. Racket in this account. So it may be choose the language. Once you've chosen the language, I don't think it asks you to do that again unless you want to change the language. So down here, I can now say define f to be lambda x. There's the squaring function. Notice that now, see, this guy keeps track of parentheses for you. Notice how nicely it is. You know, as you're typing in this REPL, it's keeping track of how parentheses balance. So you can check your parentheses as you're typing. Okay, hit enter. Now I want to call f on the input 6, for example, 36. Okay, so this is my REPL. But up here is where I can open files. This is where you open scripts. So remember in our baby REPL over here, you can run the REPL, okay, and you can run the REPL here, okay, or you can run a script by dragging and dropping a script onto this guy, okay? So you can run the REPL or run a script. Dr. Java is real nice. You can do both at the same time. This window is where you enter files, okay? So this window is a text editing window. It lets you type code. So for example, I can go up here and say, define f to be lambda x, the product of x and x, okay? Okay, now hitting enter there, I'm just typing text now. I'm not executing anything. Now I'm going to define my other function. I'll define g to be, say, lambda xy, and I'll make this the sum of x and y. Okay. Now I can save this. See, this is a file. This is actually a text editor up here. I'm going to save this to my desktop. I'm going to call it script 1.rk. The language now is no longer really called scheme. It's now technically called racket. So I'll use the extension RCT. We used to use the extension SCM for scheme. It really doesn't matter which extension I use. Right now, I'll just go ahead and use RKT for racket. So there's my script. My script has got two definitions in it. Okay. 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 Now, if I run that script, down here, I can use F because it's been defined up there. See, the definition is in my script, but now the REPL has compiled the script and digested it. So now the REPL can make you reference to these. And notice how nice this is. Like if I point to this variable y, see that arrow? That tells me where it came from, or that x. See, it's telling me where these things come from. Like down here, where did F come from? Oh, it didn't do the arrow. Oh, the arrows only work up here, okay? Like, let me define another function here. Define h of lambda, I'll make it x, y, z, and I'll make the function the product of f of x with g of y, z. Okay. Now I've changed my code up here. It's kind of like a real C. I have to run my code up here, which essentially recompiles this in a sense. So I run that code up here. Okay. Now I have h defined down here. Now here's like where did F come from? See, that's where F came from. Where did G come from? G came from over there. Where does Y come from? It's a local variable. Z is a local variable. See, so this thing, you point to variables and it's real elegant. It shows you where they come from. You point to a variable and it shows you where it's bound, where it's defined, where the variables is defined at. Okay. This is where you run your, oh, and then if I wanted to, I could actually do some calculations up here. So for example, I could say define U to be F of 3 and define V to be H of 2, 3, 4. Okay. Now, U is not known down here yet, but if I run this, all that's been run. So now down here, U, see, is 9. That's the result of having done that calculation here. When up here, the calculation is done in the script file, which defines U. And then down here, I could ask what U is, and I can ask what V is. Okay. So you create scripts up here, and then you test them down here. Now, if you ever really worked with Dr. Java, this is real similar to how we teach students how to use Dr. Java. You write your Java program up here, and then you can use the prompt down here to instantiate objects and call your methods and test your program. So you write your code up here, and now you don't have to use this down here. You could have your program do all its work up here. Like it could be that you do everything up here and that you have this one final answer that this thing produces. So you don't have to use the REPL. All the work can be done in the script. But the better way to think about languages like this is you type a bunch of definitions in the script file, then you run them, and then you test them in the REPL. Notice up here, notice how if I ask where F came from, notice how it's highlight. If I highlight F, it does three things. It shows me where F came from, but it also shows me where there's other uses of F. See how the other uses of F are being highlighted. On the other hand, if I highlight this F, it tells me where it's being used. So it points down to where F is being used. When you write 100 lines of code, this is real useful. I've never seen a Java IDE that can do this, where you can just hover over a variable and get an automatic pop-up to pointing to where the variable came from. This is kind of a neat feature. Okay. You can control where this, I think the splitter is. Yeah. All right, let's look at some other features of the language. I've sometimes told you that language 7 is C without data types. It's C without arrays or struts, okay? And our language 8 is essentially scheme without data structures. Scheme's main data structure is the list, okay? So here's how I create a list. You create a list by using quote, well, actually, let me do it down here. Quote, parentheses, 1, 2, 3, there's a list. Okay, that was a list with 4 items in it. So for example, if I ask for the length of 1, 2, see, the length is 6. Okay, now so the main data structure in Scheme is the list data structure. Now, actually, here's a beautiful thing about the Scheme language. Okay. Watch this. Okay. Now, what am I doing? I'm creating a list, and what's in the list? 1, 2, 3 items. And then one of the items in the list is another list with 1, 2, 3 items. Okay. Notice I'm creating nested lists. But what else what is this guy? If I run this, the answer is 3. See, I created a list of length 3. But what is that guy? It's a piece of code, right? This language is a tree language, or you might call it a list language. If you look up here, every line of code is a list, but the principal data structure of this language is lists. But you make something a list by putting what's called quote in front of it. So by putting quote in front of this guy here, I made him into a list. If I take the quote away, he's actually code. So the difference between code and list is the difference between a quote or not. Okay. This is actually one of the profound ideas of lists. There's actually a fancy name for it. I'm trying to remember what the word is. Programs are themselves the data structures. there's no difference between programs and data structure. Now you think about Java or C, the main data structure is an array. You can't tell me that a Java program is an array. You know, an array is a data structure that Java programs hold. But if you look at a scheme program is literally written as a list. If I go over here and I put a little tick mark in front of that, it's now a list data structure. If I delete the tick mark, it's a line of code. Okay, that's actually really amazing. And that's one of the truly profound aspects of the scheme language, that data structures and programs are actually the same thing. Every program is itself a data structure. Every data structure is itself a program. And you can do some very weird tricks with this idea. But it's got a name, and I can't remember the name for this feature. Oh, Andrew, you had a question. Just say it out loud. I just noticed I looked at,
Is
no,
that
it's not
code?
specific to interpreters, it's compilers too. You can do this with compilers. It's got nothing to do with whether it's an interpreted or a compiled language. There are both interpreters and compilers for scheme. So this trick that programs are data structures and data structures are programs is, actually, let me see if I Google it. Like,
Oh, I found the name Homo iconicity. Can anybody hear me?
Yeah, I can.
I don't know if Craft can.
so here's the idea. Scheme programs is list of symbols. But I'm trying to find the word. There's a fancy word for this concept. And I was hoping somebody would use the word in one of their explanations. Right? See, I Googled the right things. Programs as data. This is the idea. This is the word. I don't even know how to pronounce it. Okay. This is the fancy word for programs being data, that you use the same representation for data as you use for programs. Okay. Scheme invented this idea, but then at some point somebody gave it a name. Okay. So, okay. See, Lisp was the one that first did this idea. Okay. So it's a really kind of profound thing. You go over here and you can put a tick mark in front of any of these, and that tick mark says, the tick mark is called quote. So you put this tick mark here, and it's called quote. When you put a quote in front of a thing like this, it becomes a list. If you take the quote away, it becomes a piece of code. Okay. Okay. Now, we have a bunch of operations that we can do on lists. So you create a list by putting, like, by doing this, tick, then you can put things in the list. Okay, so there's the list. Obviously, I can ask for the length of a list. Okay, I can ask if a list is empty. I think you put a question mark there. Let's see. Maybe I can't, it used to be you put, maybe they dropped the question mark. Oh no, it's just, I think it's just false. Oh, no, see, this scheme has kind of an odd way. When a Boolean returns, you use true and false as keywords, but they actually print out $F. So empty 1, 2, 3 was false. Okay. Empty tick, empty pair of parentheses, true. See, there's the empty list. Okay, so tick, open parentheses, close parentheses is the empty list. Okay, you can always add things to a list. So cons is the operation for adding things to a list. So here I'm going to cons 4 onto the empty list. And I get the list with 4. Okay. Okay. And then I can also, I can cons, say, well, watch this. I'm going to cons a list onto another list. Now, what's that going to do? That's going to actually, lists don't have to be homogeneous in scheme. So now I have a list where the first item of the list is another list. So I consed the list 1, 2 as the first item in the list. Okay. Now, here's one of the beauties of this. The language has this one data structure, lists, but they actually can be also lists of lists. But if you think about it, lists of lists are exactly what we've been saying all along are trees. Okay, if you think of A, B, C, E, F, if you think about, we've said all along that that's a tree that has A as its root, A has B as its left branch, and B has C as its sub branch, and A has E as its right branch, and E has F as a sub branch. Lists and tree, once you have a list data structure, you also have tree data structures. Because as long as you can have lists of lists, this is a list of lists, and it's also, from our point of view, a tree. So scheme can do trees, which is why this thing is a parse tree. Remember, this thing, the parse tree for this is define at the root with F as left branch, lambda as right branch, then lambda has as its left branch X, and it's its right branch multiply, and multiply has as its left branch X, and its right branch X. So this thing is a parse tree. It's already its own parse tree. Okay, but it's also, notice it's a parse tree, it's a piece of code, and it's a list. Notice how there's a certain beauty to this fluidness of these ideas of lists, parse trees, programs. That's where all these things, all these ideas came out of the scheme language. Actually, it was the Lisp language back then. Lisp became scheme, and scheme became racket, is the actual history of it. Lisp became scheme, scheme became racket. So the modern version of it now is called racket. So there's also closure. Closure is another branch of the family of Lisp. But the historically most important branch of the Lisp family is Lisp, then scheme, then racket. Okay, this is the family that gave us this whole idea of trees and abstract syntax trees, and a list is a tree, and a piece of code is an abstract syntax. A piece of code can be its own abstract syntax tree. Okay, so scheme makes this really easy, makes it real kind of obvious. Okay, so down here I can ask for the length of a list. I can ask if a list is empty. I can add something to a list. Okay, so up here, here's how you make comments. So I could ask for the length of a list. We know that's one thing in our API. Oh, thanks. Let's see, where are we now? I've lost track of time. We are at what? We're over, right? Yeah. Yeah. So you guys can shout, can't you? You can unmute yourself and shout. Please just unmute yourself. You can't hear us?
I
Oh.
am
Do I have something muted that I'm not supposed to have
talking
muted?
right now.
Oh, yeah, I do. I've somehow muted you guys, and I didn't know that. I thought you guys were just being really quiet. Okay, anybody have a sense of how I fix that? Because I should fix that. Yeah, I can see the little microphones making all kinds of noise. I'm somehow muting all of you, I think. Can you guys hear each other?
Yes, we do.
Yes, we can.
Yes. And I don't hear anything. Oh, I know. My speaker's muted. Stupid. Say something.
Hello.
Yeah, my
Can you hear?
speaker was muted. Stupid me. My speaker was muted. Okay. All right. So we'll quit here. Read the stuff about scheme. We'll play around with the scheme language on next week, and we'll use scheme as a way of understanding our language 8. Okay. And yeah. So I'm sorry. I had my speakers muted, so I didn't hear what you guys were saying today. Okay. All right. So I'm going to stop sharing. And then I'll end the meeting. And if you have any kind of questions, please just send me emails and stuff like that. Okay, bye.